I just drove a nail through a charged battery, took a blowtorch to its electrolytes. I tried to melt its ceramic separator, and I even cut one in half with a pair of scissors, and nothing happened. It's not just another safer solid-state battery. It's the world's first high energy density battery that doesn't undergo thermal runaway. This is ProLogium, a company that has been deeply focused on solid-state battery development for over 20 years, with more than 1,000 patents. And it's not just their products that are ahead of the industry, their manufacturing capability is too. Since 2013, ProLogium has delivered more than 2.4 million battery cells across a wide range of applications, from drones, wearables, semiconductors, and even large-scale EV cells as far back as 2016. And now they're scaling up even further into markets like AI, robotics, maritime, defense, and aerospace. When we flew out to Taiwan and partnered with ProLogium, we asked for full access, every test, every floor, every question, and they said yes to all of it. If you only watch one solid-state battery video this year, make it this one. I'm Ricky, and this is Tuba Da Vinci. Ready? Here we go. I've toured 3 battery factories, and I was never allowed to film anything. ProLogium let me film everything. So in this video, to keep it clear, we'll call out each one of their lines, starting with their sheet-by-sheet production line for samples, second, their roll-to-roll pilot line, and finally, their roll-to-roll giga-level production line that they started in 2024. First, we got to define what a solid-state battery actually is, because right now there actually isn't a great definition. But in May of 2025, the Chinese Society of Automotive Engineers released the first official solid-state battery test. And in July here of 2026, the Chinese national regulators are going to actually incorporate an even stricter version into law. Here's how it works. Charge a battery, cut a small hole in the case, and flip it upside down. If a single drop of liquid leaks out, it's instantly disqualified. If nothing drips, the cell goes into a vacuum oven at 120 degrees Celsius for 6 hours and gets weighed before and after. Conventional liquid electrolytes use carbonate solvents that evaporate, so 6 hours of pulling vacuum at 120 degrees Celsius causes significant weight loss. A solid electrolyte loses less than 0.1% of its weight. To pass China's 2026 national standard, your cell has to lose less than 0.5%. Anything more, and you're classified as a hybrid. ProLogium's Gen 3 cells pass with an average weight loss of just 0.05%, a full order of magnitude below the threshold. Lithium-ion batteries are basically 2 chemical volcanoes pressed up against each other. The cathode side wants to release oxygen at high temperatures, and the anode wants to combust in any oxygen that it sees. Between them sits a flammable liquid electrolyte and a piece of plastic film about 20 microns thick called the separator. That plastic melts around 130 degrees Celsius, and thermal runaway, the chain reaction that turns a normal battery into a fire, kicks off around 150 degrees Celsius. This is the biggest danger of batteries, and what solid-state batteries are trying to engineer out. Replace the flammable liquid with a solid material, and replace the meltable plastic with a high temperature resistant ceramic. It sounds simple, but it's anything but.
Lithium battery chemistry have been development for than 40 years. No matter what kind of the electrolyte you use, the liquid or solid one, the industry has still no truly established no thermal runaway cell chemistry system under the standard art test.
The reason is that solid state has 4 problems, not one: safety, conductivity, pressure, and scale. The problems fight each other. The chemistry that makes a battery safer usually makes it slower to charge. The chemistry that makes it faster usually requires extreme pressure to keep the cell from falling apart. Engineering around the pressure and your manufacturing line slow to a crawl. Pick any solid-state company on Earth and they'll tell you they've solved maybe 1 or 2 of these problems. ProLogium says they've solved all 4 at gigawatt-hour per year scale in cells shipping today. ProLogium was founded in 2006 in Taiwan, and on day 1, they made one strategic decision that they stuck with for 20 years. Skip plastic separators entirely and build everything around a ceramic one. Now we're inside what feels almost like a museum. This is a sample production line that was commissioned back in 2013, and it's still in use today for engineering validation and testing. It's a great reminder that manufacturing excellence doesn't happen overnight, and it's not achieved in one leap. It's built step by step, layer by layer, over time. They've sealed the top, you saw that. They sealed one side, and so that's sealed, and this is open right here. So in this machine, they're gonna apply vacuum to
I think it's under like 95 megapascals of pressure to pull out all the air and vacuum it, and then seal this final one. This is the manual process of how they do it, which is amazing because you can actually see it, take a minute and look at it. There are automated lines that we're gonna see next. You can't even get close to it. So you can't really get hands-on with this. This is really cool to see.
Every cell they've ever shipped in any generation has used a ceramic separator. No PP or PE plastic ever.
For the day one, we have already considered not only the battery performance, but also how to achieve the real mass productions. For the material choice, the electro and ceramic separators and the cell design optimizations to manufacturing and process and also equipment.
By 2013, they were already shipping commercial cells with ceramic separators, at a time when most competitors were still running benchtop experiments in labs. They moved to roll-to-roll production in 2017, and that pilot line still runs today at 40 megawatt hours a year. Today, they've shipped over 2.4 million cells in drones, wearables, semiconductors, and large EV cells, and they're already in production with multiple OEMs. In 2024, they opened the world's first giga-scale solid-state battery factory in Taoke, Taiwan, a facility I actually got to walk around and observe for hours.
That's moving. It looks stationary, right? It's like perfect laminar flow.
And now they're ramping up their newest cell, a Gen 4 design with a 100% silicon composite anode and the highest energy density ever verified by independent lab testing. And it's a cell that we got to test, measure, and torture for the rest of this video. So let's get into the 4 problems and how ProLogium solves them one at a time. Let's start with the safety problem because it's probably the most important for consumer trust. When a lithium-ion battery overheats, 3 things happen at once. First, the charged cathode, usually a nickel cobalt manganese oxide or NCM, starts releasing oxygen at around 150 degrees Celsius. Second, the oxygen reacts with the charged anode, which is essentially a reservoir of lithium energy that desperately wants to combust. Third, the flammable liquid electrolyte between them ignites and fuels the whole thing. Once it starts, you can't really stop it. The cell heats itself, vents, and burns until everything reactive inside is gone. That's thermal runaway, and it's why a single bad cell in an EV pack can take down the entire vehicle. Conventional batteries fight this with one tool, that thin plastic separator that physically keeps the cathode and anode apart. The problem is that plastic melts at 130 degrees C, and thermal runaway kicks in at 150. So the defense doesn't survive long enough to do its job. ProLogium's answer is what founder Vincent Yang calls triple safety, 3 independent defenses, each backing up the next. Safety 1 is the ceramic separator. Instead of plastic, it's an oxide ceramic. It's hard, mechanically tough, and stable up to 300 degrees C. Safety 2 is the all-inorganic electrolyte. No carbonate solvents and no flammable organic chemistry of any kind. It's non-flammable not because it's well contained, but because the material itself can't burn. Number 3 is ASM, or the active safety mechanism. This part is pretty genius. Built directly into the electrolyte is a chemistry that activates at around 125 degrees Celsius before a runaway can even start, and chemically dismantles the charged cathode and anode, converting them into low energy compounds. The cell goes permanently dead, and it doesn't burn. It doesn't really even get particularly warm. ProLogium's Gen 4 cell is the first lithium battery in 40 years to pass the gold standard ARC, or accelerating rate calorimetry test, without going into thermal runaway. And the result has been independently third-party tested. In ProLogium's reliability lab at their HQ, I watched as they tested 5 different ways to absolutely destroy a battery. First was the oven test. A live cell goes into an industrial oven that ramps up to 280 degrees C, almost twice the temperature where a conventional battery would already be on fire.
I can feel the heat coming off of it, even through all that. Look at the level of insulation, how thick that wall is. This is what 280 degrees Celsius does after over an hour. So it's fully charged. Set into the oven at 280. And this is just an example of the safety of the cell. So no thermal runaway events, nothing happened, all safe.
ProLogium cell sat there for hours and came out structurally intact. The damage was irreversible, but the cell was completely stable.
By far one of the coolest tests you'll see. This is a nail penetration test on a solid state battery. Let's see how it fares. Nothing happened with what you want to see, but the orange line here is voltage, It started nice and steady. As soon as the nail punctured it, the voltage dropped. That's what you want to see, what you'd expect, because there's no voltage potential anymore. The two ends are now shorted. Now if you look at the nail puncture test, you'll see two thermocouples coming off of it. That's the two different temperatures here. The red is the nail temp, that the thermocouple on the nail, it's rising, and the blue is the cell temp. That's the thermocouple on the cell, also rising. Exactly what you'd want to see if you had a puncture. And the battery is safe. Goodbye forever. Here we go.
Third was the external short circuit test, a direct dead short between the terminals at a full state of charge. A conventional lithium ion at 100% state of charge would go very wrong within seconds. Next, we tested the electrolytes. Side by side, a beaker of conventional carbonate-based liquid electrolyte and a sample of ProLogium superfluidized electrolyte. We hit both with a propane torch. The conventional electrolyte ignited pretty much instantly, and it burned vigorously. ProLogium's didn't ignite and didn't smoke. Next, we tested the ProLogium ceramic separator against a conventional separator. I used the same propane torch, and you can see immediately the difference between a ceramic separator and a PP polypropylene or PE polyethylene separator. It didn't melt, it didn't shrink, and it didn't ignite. And after we pulled the flame away, the separator was still electrically insulating. It's still doing its job. And then finally, I cut a cell in half.
Part of the challenge with ceramic separators is brittleness, right? So things like this, even, hitting it like this would potentially cause issues. It could cause a short inside of the battery, but this is working without any problems. Now, I can just cut it, right? Yeah. This is, this is one of the most wrong feeling things I think I've ever done. But I'm gonna cut this cell. You ready? Here we go. I just cut that cell apart, and with what's left, it's still working.
Very interestingly, if we slow this down, you can see that the LED goes out when the metal in the scissors shorts the two electrodes, resulting in a voltage potential between the two dropping to zero. But once I finish the cut and the scissors are removed, the short is removed, and the cell recovers and the light comes back on. That's a clean cut through both current collectors, anode, cathode, and separator. And other than losing half its capacity, the cell kept on going. And most importantly, nothing leaked. That solves problem one, but safety alone doesn't sell batteries. If it takes 4 hours to charge or costs 4 times as much, no one's gonna buy it. Which takes us to problem two, conductivity. How fast lithium ions can actually move through the electrolyte. It's the second hard problem, and it's proven to be quite difficult for solid-state batteries. In a normal liquid electrolyte battery, lithium ions and their negatively charged counter ions both move freely through the liquid. But under heavy current, the two species start drifting apart, building up concentration gradients that fight effective transport. Battery engineers call this concentration polarization, and it's a big reason your phone charges fast to 20% and slows to a crawl at 80. Conventional solid-state batteries fix concentration polarization by locking the negative ions into a rigid crystal lattice. Now the lithium moves, but has to hop between fixed atomic sites, and every hop costs activation energy. The result is dramatically lower conductivity, which means painfully slow charging for the end product. ProLogium says that their electrolyte is neither.
It is not a conventional liquid and not a rigid traditional solid-state one. It is the third type of the electrolyte created through the human innovations.
They call it a superfluidized all-inorganic solid-state electrolyte. And as the name suggests, it's an all-inorganic solid electrolyte that has been superfluidized, exhibiting non-Newtonian behavior. The material has the consistency of soft pudding, and when subjected to higher shear rates, the viscosity decreases. The technical term is shear thinning.
ProLogium technologies is designed to be combined the strengths of the both of systems. Our superfluidization of inorganic solid-state electrolyte can deliver high ionic conductivity like the liquid electrolyte, high lithium ion transportation efficiency, and low polarization like the solid-state electrolyte.
ProLogium's founder, Vincent Yang's analogy was a relay race. The lithium ion never has to travel far through the electrolyte. It hands off to its neighbor, who hands off to the next, in short hops through a coordination network that dynamically reconfigures around it. The negatively charged counter ions are everywhere around it, but they don't run laps. They just step aside locally to let the lithium through.
The whole point of the electrolyte is to conduct, right? So this is measuring the conductivity for the traditional battery electrolyte, and this is the ProLogium electrolyte over here. And if we convert both to the millisiemens per centimeter scale, this becomes 4.8 and this is 55. So an order of magnitude, over 10 times higher conductivity for theirs as well. So we just showed it was safer and 10 times the conductivity of the traditional electrolyte.
But the electrolyte alone isn't enough. Lithium still has to cross from the electrode to the electrolyte itself. And at that boundary, most solid-state cells completely fall apart. ProLogium's answer is a thin engineered coating on each electrode they call IDL, short for ion diffusion layer. Its only job is shepherding lithium across the boundary without resistance, cycle after cycle. Solid-state batteries fail at this interface. The interface we've always talked about is the trickiest part when it comes to a full solid-state battery. And ProLogium designed their layer to specifically solve this. The conductivity number, 57 millisiemens per centimeter at room temperature, was measured in ProLogium's own lab, witnessed and certified on-site by an agent from SGS, the Swiss certification body. SGS didn't have the equipment for this kind of test, so they sent a representative to verify ProLogium's own measurement. Still independent third-party validation, just done a little differently than usual. About 5 times faster than the best liquid electrolyte, and orders of magnitude faster than any conventional solid. Even at negative 20 degrees Celsius, it still measures 12.5 millisiemens per centimeter, retaining over 95% of its capacity in cold weather, where most batteries lose 30 to 40%. So then this translates to 5 to 80% fast charge in around 6 minutes. And if you're keeping score at home, high conductivity, full transference, low polarization, cold temperature performance, that's a list of properties no liquid and no salt has ever delivered together. Which brings us to problem number 3. The other major type of solid-state battery electrolytes being pursued is the family of sulfides, which offer high conductivity comparable to liquid, but with one massive engineering catch. According to a 2026 paper in the journal Joule, sulfide solid-state cells need an operating pressure of about 800 atmospheres. It's about 12,000 psi, the kind of pressure you'd find 8 kilometers underwater. And they need 6,000 atmospheres just to manufacture them. Why? Because sulfide particles expand and shrink during every charge and discharge cycle. They lose contact with each other, and the only way to keep them touching is to mechanically compress the cell from the outside forever for the rest of the life of the battery. Now this means higher mass, higher cost, and you can't even use them on phones or drones because the pressure system alone would weigh more than the battery itself. ProLogium superfluidized electrolyte handles this completely differently. The gel texture network self-maintains contact through every charge cycle without permanent external compression. But there's a nuance worth getting right here. Every brand new battery, solid-state or not, goes through a process called formation. It's the first few controlled charge cycles right after the cell is built, where the chemistry settles into its final working geometry. The active materials expand in place for the first time, and the internal interfaces lock in. Think of it like breaking in a new pair of shoes. But once that formation finishes, typically a handful of cycles, that pressure comes off and the cell operates at exactly 1 atmosphere for the rest of its life. A gentle squeeze during break-in versus 800 atmospheres forever. It results in lighter, safer, and cheaper packs, and that unlocks the real market potential of next-generation batteries. Which brings us to the 4th problem, and the one that actually killed most solid-state batteries that I've ever tried to ship. And that would be manufacturing. Here's the dirty secret of solid-state batteries that no one talks about. The chemistry has actually kind of been solved for a while now. The hard part, the part that is really hard to get right, is how to take that idea and produce it on a massive line at scale. How do you mass produce a brittle ceramic separator the size of a phone screen on a moving production line without cracking it? There are 2 competing approaches. Most American and European competitors use a process called sintering. You heat ceramic powder to over 1100 degrees Celsius until the particles fuse into a sheet. It's slow, it's offline, and it poses a major limiting factor in the manufacturability of solid-state batteries. ProLogium chose differently from day one. Their ceramic separator is made by a wet film coating, the same process used for cathode and anode coating in any conventional battery factory. You mix the ceramic into a slurry, you coat it onto a moving roll of metal foil, and dry it.
So this is the input anode on the current collector and the anode. And if you look right there, That is the separator, the solid state separator applied.
This proprietary process is one of the key breakthroughs that allows ProLogium to produce batteries roll to roll at large scale, a process we saw firsthand. And looking at this factory, you can see how much thought was put on speed.
So this is anode,
Yeah, and
ceramic, cathode. And they all have different requirements, right?
Different
Okay.
temperature.
Most of this line you see here are heaters, because the faster that roll is moving, the less time you have to dry it. And the results are absolutely amazing. ProLogium's pilot ceramic separator line runs at 6 meters per minute. Their gigascale line runs at 55 meters per minute, nearly an order of magnitude faster than any sintering approach could even imagine reaching. Then there's drying.
This oven behind me is 24 meters long, but by the time this roll has snaked through, this entire roll is snaked through, it'll travel 240 meters up and down. This is that final drying stage. And because of this system, the speed that it goes through, and this orientation and some of the other secret sauce they have, they're able to get the humidity down in about 8 minutes, what normally takes most battery manufacturers 8 hours. And this is critical. At this point, when the roll comes out of this, there's no moisture because it's going into the dry room and continued all the way to assembly. So you can't have any moisture left after this step.
Even the cell housing is different. Where conventional batteries weld a separate aluminum pouch around a finished electrode stack, ProLogium prints the housing directly onto a cell using a proprietary silicon-based material that they call Lithium.
You can kind of see it's this outer boundary. It acts as a couple of things. It's an adhesive layer that helps them to stack these cells together. So this would be the cathode to stack with the anode. And it keeps out moisture. It's like a barrier.
It acts as an additional separator at the edges of every stacked cell, preventing short circuits both during production and through the life of the battery. Patented all the way back in 2010, and that same architecture with an additional edge separator has since been adopted across the entire solid-state industry, before most people even were thinking of solid-state batteries. Now, this might be a part of their technology that I kind of didn't appreciate until I saw it in person. Think screen printing on a shirt. That's kind of what it reminded me of. But they're doing this on a roll-to-roll process. Conventional battery production steps like electrolyte injection, right, where you get the pouch and then you squeeze the liquid in, vacuum impregnation, second formation cycles are completely eliminated. The dry room footprint shrinks dramatically. And as amazing as the access for all the safety tests and propane torch tests were, this right here might be even more amazing. This is the answer every battery analyst has been asking for 20 years. How do you take something so complex, brittle ceramics on a roll-to-roll process, the stuff that makes solid-state batteries so appealing, and possibly do it economically at scale? And while we've covered so many companies that make a lot of noise, ProLogium is already producing nearly a gigawatt-hour a year, with plans to scale that to 3 here in Taiwan.
The project growth strategy is not only development of better batteries. Our goal is to build up the next generation battery platform that can be mass-produced at a scale and offer the affordable cost and applied into the many different markets.
Oh, and they're also planning their next factory in Dunkirk, France. And then there's the number one comment I've gotten over the past 2 months or so, which is weighing the cell and getting actual testing for the watt-hour per kilogram energy density. Well, I did that too. The cell that I'm holding here was verified by the German testing body TÜV Rheinland, but I actually got to test it myself.
All right, so we've shown you some safety. We've shown you how it's made. But the question you're probably wondering, and I always have been as well, is what about the energy density? Well, you need 2 things for that. You got to figure out how much this weighs, weigh the cell. And second, we have to test to see how much energy it can store and how much we can get back out. So let's actually weigh this. 1697.5, 1.6975 kilograms. Okay, so they're doing the energy density test to see just how much energy they can put in and get back out of these cells. So we'll go look at the monitor and see how they fare. We started with a cell here with a voltage starting at 4.1 volts and ran the test until the voltage dropped to about 2 volts, and we got out 612.37 watt hours. So it's 12.37, which gives us a energy density of 360.748 watt-hours per kilogram. That is a number you've probably been thinking about. I know I have. And with validation and testing, we can actually show you something that you've probably been thinking. That number is the highest I've seen. Amazing. So now this is the volumetric. Okay, so volumetric energy density of 898 watt-hours per liter. Also the highest I've ever seen.
So how did they hit that number? Well, two design choices working together. A nickel-rich cathode called NCM955 that's 90% nickel, 5% cobalt, 5% manganese, the most aggressive nickel-rich chemistry shipping at scale, paired with a silicon composite anode that stores roughly 5 times more lithium per gram than graphite. For example, the best cells in EVs today are around 270 watt-hours per kilogram. ProLogium solid-state cells beat that by 20 to 30%. And the roadmap goes even further. They've already reached 380 plus watt-hours per kilogram. And it's manufacturing ready, not a lab experiment. With a full lithium metal anode on the roadmap, they could push that number even higher. So what does it mean for EVs? Well, 30% more range from the same battery weight, or 30% lighter battery packs, depending on how you look at it. What about cycle life? While the cells were still being tested at scale by automotive OEMs as we speak, ProLogium told us that they comfortably exceed standard automotive requirements matching cells today.
We believe that only the balance and the practical next generation battery solution can truly support the development of the industry. Such a solution must combine the high safety, the high energy density, and stronger performance, affordable cost, and scalable mass production capability.
All of these numbers that we've shown are third-party verified. I quickly realized why ProLogium was so transparent with me. It's because they've done so much third-party validation already. Seriously, it was enough to make my head spin. When I met with ProLogium in Taiwan, I didn't really even have a definition for what a solid-state battery actually was. And now I've tested it, I've punctured it, I've cut it in half, I've weighed it and measured it. And aside from working with EV manufacturers, they're also working with key players in other emerging markets too, and a French gigafactory breaking ground for the European market. It turns out 2 decades of doing the hard work, stacking innovations on top of each other, and quietly being brilliant really pays off. I've never worked with a more transparent company, I've never had more access, and I've never had more of my questions answered. And I've just been absolutely blown away. One other thing I learned doing this video was I saw this bag of potato chips sitting on a lot of the machines in the factories and in the labs. And I asked them, like, what is this? So if you look right there, that translates to well-behaved. This is a popular children's snack. And the idea is that this is made for good boys and girls. And so it's a Taiwanese tradition to put this on machinery to make sure that the machines are well-behaved and work well. Maybe it's a secret to all the genius that happens here in Taiwan. So if it's good enough for Taiwan and ProLogium, it's good enough for us. We're gonna put this on our hardware as well. So what do you think? How amazing has this been? And what questions do you have for the team? If you think we've earned it, burn that like button and puncture that subscribe button so you don't miss our future deep dive videos. Huge thanks to ProLogium. Thank you for all the time and coordination and for giving us so much access. This was one of our favorite videos we've ever made. All right, I'm Ricky. This has been Da Vinci, and we'll see you on the next one.